So we talked about alcohols behaving as a carboxylic, as an acid and a base. And this slide is relating that a carboxylic acid can also behave as an acid or a base. And here we can apply the concept that an acid, a Lewis acid, is going to be an electrophile or electron pair acceptor and is going to be positively charged, either positively charged, partial positively charged, or have less than an octet. So we're going to look at how the molecule behaves and what concept is being applied when it behaves as an acid and which concept applies when it's behaving as a base. Okay, let's write this out. Okay, so Lewis acid equals electrophile has a positive, partial positive, which is symbolized by a lowercase delta, and or less than octet. Okay, so our Lewis acid is an electron pair acceptor. And here we have the carboxylic acid listed as an acid, and we can define its behavior by our concepts. So if it's behaving as an acid, it must either be positive, partially positive, or have less than an octet. And in this case, the proton is partially positive because of the polar bond to oxygen, where oxygen is much more electronegative than hydrogen. So when the carboxylic acid behaves as an acid, the partially positive hydrogen is the acidic atom. And then for the Lewis base, this is a nucleophile. That is either negatively charged, has a pi bond, or a lone pair, LP. And so when we look at the base, we see that it is both negative and that it has lone pairs. So our base is acting as a nucleophile, having the lone pairs, and what the acid does is accepting electrons while the base is donating electrons. And that is displayed by the curved arrow showing electrons from the oxygen of hydroxide going to the hydrogen of the carboxylic acid. And because hydrogen can only have one bond, the bond between the oxygen of the carboxylic acid and the hydrogen breaks. We can also look at the concept of deciding what side of the reaction is favored. Reactants, as written from left to right, are the reactants on the left favored or the products on the right favored for the equilibrium of this reaction. And I said previously that in order to do this, what we should do is to give the pKa's of the acids of the acid in the reactant and the pKa of the acid in the product, and that the equilibrium of the reaction will favor the side of the reaction that has the acid with the highest pKa. So for the carboxylic acid, the pKa is going to be 4 to 5. And for the acid in the product, which is the water, because it has one more hydrogen than the hydroxide, so that indicates that it's the conjugate acid, then the pKa of water is 16, which is greater than the pKa of the carboxylic acid. And therefore, as the arrows show, the products as written, the products on the right, are favored in the equilibrium. If we look at the reaction below, where the carboxylic acid is acting as a base, we can show that it is the action of the base is that the carboxylic acid has lone pair and so is allowed to act as a base because of the lone pair. And because it has this lone pair, the lone pair can be donated to a partially positive hydrogen. And we know that the hydrogen is partially positive, even though the oxygen is formally positive. The oxygen is still more electronegative than hydrogen. And so we still have a dipole, and the oxygen, because it's more electronegative, while it has a formal positive charge, will steal more of the electrons from the hydrogen bonds, O to H bonds, so it actually has a higher electron density on oxygen than on hydrogen because of electronegativity. And so formal charge does not show you where electron density rests. You have to take into account electronegativity. You have to draw your dipoles to figure out which atom is going to be the electrophile. The atom that is the most electron deficient, the least electronegative, is more likely to be the electrophile. So draw your dipoles. Okay, so hydrogen is going to be our acid atom, our electron pair acceptor. And when hydrogen accepts the electron pair from the oxygen of the carboxylic acid, then the bonding electrons to the protonated water breaks and we receive simple water. So in the products, the carboxylic acid is the acid because it has one more proton than in the reactant, and the water is the base. And then determining which side of the reaction is favored, we can consider pKa, where a protonated acid has a pKa of or I'm sorry, protonated water has a pKa of approximately -1. And the protonated carboxylic acid, according to the text, has a pKa of approximately -6. Therefore, the reaction should favor the side with the higher pKa, and in this case, that is the reactants on the right are favored. And your book correctly just indicates that with the reaction arrow given. Okay. Too much writing. I'm going to erase all of this and we're going to start over.